Hi everyone, today another video in the Kinetics series looking at rates of reaction and the Arrhenius equation. So we said in the previous video of this series that the main factors that affect the rate of a chemical reaction are surface area, catalysts, temperature, pressure and concentration. And we also said that the rate of a reaction was defined as the change in concentration of a specified reactant or product with unit time. So how much does the concentration of a reactant fall by, or how much does the concentration of a product increase by with in a certain time? Now reaction rates are measured in moles per decimeter cubed per second. So I think normally that concentration is measured in mole per decimeter cubed. Our definition is it's the change in concentration with unit time or per unit time. So we have our moles per decimeter cubed and then divided by unit time, which is in seconds, moles per decimeter cubed per second. So if we consider the reaction A plus 2B goes to C, we can draw a graph of concentration of each species against time. Now our reactants are obviously going to fall in concentration. Our products are obviously going to rise in concentration. But as we said last time, our reaction rate isn't constant across a reaction. If we increase the concentration of something, our reaction rate increases, but our reactants get used up, and so eventually there's less around, the collision frequency decreases, and hence we end up with a slower rate towards the end. And so these curves that we've drawn are they're curves, they're not straight lines. That's because they typically, in terms of either the product or the reactant tends to fall slightly quicker at the start because there's a lot more of it around, the collision frequency is higher, and then towards the end when it's being used up, the collision frequency is a lot less because essentially the concentration of that is a lot less. Conversely, with our product C, you can see that the rate of the increase of that starts off quite quickly, and then it tapers off towards the end. You'll also notice that the B concentration line is twice as high as the A. This is because it's a A plus 2B reaction, so we have twice as much B, but also because you can see that the decay of the B is twice as fast as it is for A. It's decaying faster, it starts higher. Again, because we have A plus 2B. Now, often we're interested in the rate at a particular point, at an instant, rather than over a longer period of time. And so we want to find something called the instantaneous rate, the rate at a specific time. And so to find the rate of change of our concentration at a particular instant, we draw a tangent to the curve at that time and find the gradient. Now, if you're not so mathematically minded, a tangent is a line that touches a curve only at one point. And then we want to find the gradient of this, so we typically draw our tangent nice and big as shown is on the right. We draw our tangent here, it just touches x equals 3. And you can see we draw our line quite far sort of backwards and forwards. And then the gradient, remember, is the change in y divided by the change in x. So for a concentration time graph, it is the change in concentration divided by the change in time. You can see from the units, concentration being moles per decimeter cubed, time being seconds, that this gradient, change in y over change in x, or change in concentration divided by change in time, is going to give a unit of moles per decimeter cubed per second, and that's our rate of reaction. And so to work out the instantaneous rate, you draw a tangent at a particular time, and then calculate the change in y over the change in x, the gradient. There's also another type of rate called the initial rate, and this is exactly as it says on the tin. This is the rate at t equals 0. So we still plot our curves for the whole reaction, and then typically we do this measuring a product. And so if we look at the curve for product C, what we would do is draw a tangent, but at t equals 0. And that's called the initial rate because it's at the start of the reaction. Typically this is a fairly easy one to measure because normally you know exactly how much reactants you started with. You also know exactly how much product you start with because it's 0. So this now brings us into something called the Arrhenius equation. Now, as we said in the previous video of this series, the rates of chemical reactions can increase greatly for a relatively small rise in temperature. A pretty small temperature change can give a massive increase in the rate of the reaction. This is because as the temperature rises, the number of collisions between reactant molecules will increase. If we increase the temperature, the molecules are going to move a bit quicker, they have more energy, and so they're more likely to collide with each other, and so our collision frequency increases. But actually this increase is not enough to explain the massive increase in rate. And the key thing from this is that increasing the temperature also increases the number of collisions that have energy greater than the activation energy. Now remember from the previous video that the activation energy was the minimum energy required for a successful collision. And so if we have an increase in temperature, we have many, many more molecules that now have energy greater than this activation energy. And that's the real key thing for the increase in rate. We also saw that we could draw Maxwell-Boltzmann distribution curves, and that the shape of this curve changed when the temperature changed, and hence the energy distribution changes with the temperature. We saw at higher temperatures that the peak of the curve was slightly lower down and was slightly to the right. The curve becomes slightly flatter and broader. And what this meant was that essentially we have many more molecules with energies greater than the activation energy, and hence there's a large increase in rate for a pretty small increase in temperature. Now, this fraction of molecules that have energy greater than the activation energy is given by this mathematical expression here, E to the negative EA over RT. So that fraction there, the negative EA over RT, all of that is raised in the power of the exponent. And so we have EA being our activation energy, R being the gas constant, 8.314, and T being the temperature. And so that expression there would give you the fraction of molecules that have energy greater than the activation energy. Now the activation energy can be linked to the rate constant, K. Remember that small k is a rate constant, big K is an equilibrium constant. But the activation energy can be linked to the rate constant by the Arrhenius equation. And the Arrhenius equation is shown below. It's K, the rate constant, equals A, something we call the pre-exponential factor, multiplied by that fraction of molecules with energy greater than the activation energy, E to the negative EA over RT. So the Arrhenius equation is K equals A, E to the negative EA over RT. Now we have to just be careful with units on this. Activation energy has to be in joules per mole, and the temperature has to be in Kelvin. Now A is the pre-exponential factor. We've said that this exponent that we have in the equation is the fraction of molecules with energy greater than the fraction of molecules with energy greater than the activation energy. This A relates to the number of collisions per unit time, irrespective if they are successful or not. So A is literally telling you how many collisions are happening per unit time. It doesn't matter whether those collisions are successful, i.e. whether they collide in the correct orientation, whether they have enough energy. It's just simply how many collisions are happening. We then have this exponential part of it, which is again the fraction of molecules that have energy greater than the activation energy. And so hopefully that you can see if you multiply the total number of collisions by the number of molecules that have this minimum energy requirement, that's going to give you essentially the rate of successful collisions, which is our rate constant, K. And so K is the number of successful collisions per unit time. And we can also see here that A is the pre-exponential factor. It has the same units as K. And at the actual exponential term, if you look at the units of your activation energy, temperature, and the gas constant, that is actually dimensionless. It doesn't have a unit. Now the equation can also be written in what we call a logarithmic form. We take logs of both sides of the equation. And the reason that we can do this is because a logarithmic equation is a much easier way to work with the Arrhenius equation. The Arrhenius equation in its original form, K equals A e to the negative EA over RT, is this curved shape. It's quite difficult to work with and extract data from and plot, whereas a logarithm, the logarithmic version of this, is a straight line. So if I take logs of both sides, natural logs, ln, I end up with ln k, the log of k. I also end up on the right-hand side with the log of a. Now, if you remember our laws of logarithms, essentially we take the log of the whole right-hand side, so we'd get the log of a e to the negative ea over rt. And then using the law of logs, because we have a multiplied by this exponential, we can write that out as a sum of logs. So we'd have the log of a plus the log of e to the negative ea over rt. Now the natural log, ln, is the inverse of the exponential e. And so those two things essentially cancel out. And so what you're left with is ln k equals negative ea over rt plus ln a. Now this has exactly the same form as the equation of a straight line. Remember that a straight line equation is y equals mx plus c. And so hopefully you can see that you can start to link some of these quantities together. We can say that our y is the same as ln k. We can say that our c is the same as ln a. And so if we plot y equals ln k, and we say that our x-axis is 1 over t, well then our gradient, the m, if our x is 1 over t, that must leave that our m is the negative of ER divided by r. It's everything else that we haven't dealt with in the equation. And so if we plot ln k versus 1 over t, the value of our activation energy, EA, can be found from measuring the gradient. Remember, the gradient is the change in y divided by the change in x. And so our activation energy can be found by measuring the reaction rate, K, essentially, for different temperatures. And remember that C is the intercept, where it would intercept the y-axis. Now, log values have no unit. So the value of ln A, the value of ln K, they have no unit. The unexponentiated quantities do. So A and K do have units, whereas ln A and ln K don't have a unit. Now, EA, the activation energy, will have units of joules per mole, and it will most likely need to be converted into kilojoules per mole, because typically the values are quite big. So, just another example of how to do this. We start off with Arrhenius equation, K equals AE to the negative EA over RT. We take the log of both sides, and then we can use our law of logarithms to split up the right-hand side. Because it's a multiplication between A and the exponential part, we can write that as the log of A plus the log of the exponential part. The log of the exponential part, the log and the exponential cancel out, so we're just left with negative EA over RT. And then we can just rearrange the equation to put our EA over RT first. So we have ln K is negative EA over RT plus ln A, and that matches the form of a straight line equation, y equals mx plus c. And then we can plot y as our ln K, x as 1 over t. That leaves our intercept, our y-intercept c, as being ln A. Remember that A was the pre-exponential factor, the number of collisions that happened, irrespective of whether they were successful or not. And then that leaves our gradient as being everything else we haven't touched here, which is the negative EA over R. And so if I plot this, essentially what I have to plot is the ln K. So essentially to do that, we must have measured K, the rate. To plot 1 over T, we must have measured the rate at different temperatures. And so if I plot my rate constant, the log of my rate constants versus 1 over temperature, I have a straight line, which is going with a negative slope. The gradient, remember, is the change in y over the change in x. And so that gradient is equal to negative EA over R. And so if I wanted to work out what my activation energy was for a reaction, I could take the value of the gradient, times it up by R, and then take the negative sign of it, and that would give me my activation energy. And so you can see some other graphs here on the right. So that the graph at the bottom left is the logarithmic form of the Arrhenius equation. You can see it's pretty easy to deal with because it's a straight line. The one at the top right is just our normal Arrhenius equation, plotting K versus temperature. And because it's an exponential equation, essentially it has this exponential form of the curve that rises. And that's more difficult to work with and extract data from. And then just at the bottom, I've just reminded you of the Maxwell-Boltzmann distribution curves, and how if we have a very small change in temperature, this can lead to a very, very big change in the rate of reaction. This links into the Arrhenius equation because the temperature quantity is within the exponential. And so a very small change in the temperature is going to give a big change in the rate of reaction because it changes the exponential factor by quite a lot. And so if we plot that on the Maxwell-Boltzmann distribution curve, we can see that the curve that's labelled T2 is lower down and further to the right than T1 because T2 is higher than T1. So our most probable energy, the peak of that curve, is a higher energy. And it's also lower down because now we have more particles that have, or more molecules that have greater energy. And the key thing is that we have more molecules that have energy greater than the activation energy. And we can show that by showing the area under the curves for the point past the activation energy. Remember that the area under the curve is the number of molecules. And you can see that that's much bigger for the higher temperature than it is for the lower temperature. So therefore there are more successful, more effective collisions. So time to have a go at some questions. Some mathematical questions here, basically using the Arrhenius equation to be able to work out some values. And so if you want to have a go at the question, pause the video and the answers will be on the next slide. So the first question was to calculate the proportion of molecules with an energy greater than the activation energy which is 100 kilojoules per mole at 300 Kelvin and at 310 Kelvin. And so remember that our proportion of molecules that have an energy greater than the activation energy, that's the same as saying the fraction of molecules that have an energy greater than the activation energy. And so we have to use that exponential part of the equation. Remember that the fraction that had energy greater than the activation energy was the e to the negative EA over RT. So we're given our activation energy. Remember that we have to convert our activation energy into joules per mole rather than kilojoules per mole. That's just to make the units cancel out with R and T. Typically the unit of R has a joule in rather than a kilojoule. And so we need our activation energy to be in joules because remember that our exponential quantity is dimensionless. So we have our activation energy, which is 100 kilojoules per mole. So that's 100 times 10 to the 3. And on the bottom we have our gas constant, 8.31, and times the temperature, which again remember has to be in Kelvin, so 300. And so if we do that, and we do that to the exponential to the minus of all of those numbers, we end up with 3.8 times 10 to the minus 18. Another way to say that is that 38 in 10 to the 19 molecules have an energy greater than the activation energy. So as you can see, that's really not a lot. If we do the same calculation now for 310 Kelvin, we end up with 1.38 times 10 to the minus 17. Essentially, 14 in 10 to the 18 molecules have energy greater than the activation energy. Now, while that doesn't necessarily seem like very much difference in terms of they're quite small numbers still, it's actually a 3.6, nearly a 4 times difference in the number of molecules that have greater energy greater than the activation energy for simply just a either a 10 degrees Celsius or a 10 Kelvin change in temperature. So a very small change in temperature has produced this nearly 4 times difference in the number of molecules that have greater activation energy, and therefore a 4 times difference typically in the reaction rate because of the effective collision there. Then question 2 was to find the activation energy for a reaction where we were given these various quantities. So this is to use the Arrhenius equation, K equals AE to negative EA over RT. Now, like I said, the logarithmic version of this equation, while it's much easier to deal with in terms of plotting a graph, it's typically also a lot easier to deal with when you're calculating things. So I would recommend to do this as a logarithmic equation. And so we take logs of both sides. We have ln k is equal to the log of AE to negative EA over RT. We use our law of logs to separate that right-hand side, make it an addition. And we also note that the log of the e, the log of the exponential part of it will cancel out. And so we end up with ln k equals ln a minus EA over RT. Now we want to find our activation energy, so we need to rearrange our equation to be able to find EA. So I'm going to rearrange it to have EA over RT as the subject. To do that, I have to add EA over RT to both sides and minus ln k from both sides. And we end up with EA over RT is ln A minus ln K. Now we can use our law of logarithms again. Remember that when it was a multiplication, we could write that out in logarithms as a sum, ln of this plus ln of that. The same goes for subtraction, but this time it's a division. So we have ln A minus ln K, and that's actually the same as ln A over K, A divided by K. And then it's quite simple. If I want to just find the activation energy, I need to multiply both sides by RT. So I have that EA is RT ln of A over K. And then simply we just have to put our numbers in, just being careful of our units. So we can see that our molar gas constant R has a value of 8.314, and look at the units, joules per mole per Kelvin. So we need to make sure that essentially our activation energy will be given, when we calculate it, will come out as joules per mole. We have our temperature, which was given to us in Kelvin, but it must always be in Kelvin. You can see that because our molar gas constant has a unit of per Kelvin. So to make the Kelvin part of it cancel out, we have to have our temperature in Kelvin. We were given our rate constant and we were given our pre-exponential factor, both in mole per decimeter cubed per second. And so we put these numbers into our equation and we find out that our activation energy comes out to be 45,230 joules per mole. And this is what I was saying on one of the previous slides, that if you work out an activation energy, typically they are pretty big numbers, and so it's better to write them as kilojoule per mole. So divide by 1,000, and we end up with an activation energy of 45.3 kilojoules per mole. So if you're working out an activation energy, always double check the units that we're dealing with. Typically the units of the gas constant would be the main one to look at, whether it's in kilojoules or joules. Normally it's in joules. And so therefore, if you're working out an activation energy, the answer will come out in joules, but typically they're very big. So I would always convert them into kilojoules just to make them look nicer. If, for example, we were calculating a rate constant from the Arrhenius equation, we'd have to make sure that our activation energy, even if it was given to us in kilojoules per mole, is in joules per mole to make sure the units cancel out with the R, which is typically has a unit of joule in there. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on the tuition website. I offer online tuition for chemistry, so please check my tuition pages for the process and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.